All right, Chemistry 3111. We're going to start off with question 21.72, which is a really great question. We're starting with 3-pentanone, and then we want to make 3-hexanone. So essentially, all you need to do is add an extra carbon here, right, to the molecule, like this carbon that I've added here. So, in terms of your retrosynthesis, maybe you could think of something like this, and if we were to break that bond, the way that I thought about this first was like a Michael reaction. Because if we had this molecule, if we had a Michael acceptor like this, then we could just use a cuprate, right? All you have to do is treat this with dimethyl cuprate followed by aqueous acid, right? And that would give you the desired products. And then the question becomes, well, how do you get from here to here? Right, and that's not that much of a stretch. I mean, all you have to do is to make the alpha bromoketone. So for that, you just treat it with a catalytic amount of acid. You know what? Let's write every step out. So first, you're going to treat it with a catalytic amount of acid and bromine, and that's going to give you, again, the alpha bromoketone, like this. Then you would treat it with a base like pyridine or lithium carbonate. So let's see here. Let's just use pyridine. That seems to be the most popular. Then you end up making a Michael acceptor, right? So now you've got Michael acceptor. And then all you have to do, again, is treat that with a cuprate, which is a soft enough nucleophile that it will do the conjugate addition. So we're going to treat this with the dimethyl cuprate and then with H3O plus in the end. Now, I thought of this, and I don't like to look at the solutions manual very much, so I kind of came up with this one first, and then I was doing another problem, and I thought, oh, I know another way to make this molecule. And let me show you what the other option is, which is perfectly reasonable. I'll do this one in blue ink. And I don't know why I didn't think of this one sooner, but if you want to make this compound, then I thought, well, what if we were to start out with propionic acid, right? If you had propionic acid, then you could just treat that with a cuprate. I mean, first you'd have to make the acid chloride, right? But then you could just treat it with the cuprate, and that's going to give you, that's going to install this group here, the propyl group, right? So then the question becomes, well, how do I get from here to here? And the answer is a Baeyer-Villiger, right? And it's easy because you don't even have to remember the migratory aptitude, since both of these groups are identical. All you got to do is treat it with a peroxy acid, so RCO3H, and then we would end up with this ester, right? And you can just hydrolyze that in acid. So we'll do acid and we'll cook that up. And then you end up with propionic acid. Then all you have to do is treat this with thionyl chloride, SOCl2, to make the acid chloride. And once you have an acid chloride, the world's kind of your oyster then, right? Then all you have to do is treat it with propyl, the propyl Gilman reagent like that, and that would work too. It's just an option, And again, either one of these options is perfectly reasonable. I'd say there's neither that's better than the other. I'd say they're both perfectly reasonable ways of doing this chemistry. All right, another one I wanted to look at with you was question 21.73, which I also thought was challenging, but a good problem nonetheless. So this is question 21.73. They just kind of give you a bunch of different reactions, and you have to come up with the reagents. So the first one, we start with this molecule, which is ethyl benzoate. There's no enolizable protons in it. And you want to make this compound. So you want to make this beta keto ester like this. Okay, here you go. And then you want this. Okay. So, I mean, this is nothing more than a Claisen condensation, right? So this is I'll write it below after. But you know that the enolate that you would need would be this, right? You'd have to treat it with this enolate, okay, like that. But, where are you going to get that from? Well, you would get that from, I didn't give myself enough room here. But you would make that from this compound, so from the ethyl ester, and then you would just treat that with LDA. So you take that, you treat it with LDA, you make the enolate, and then you follow that up with acid. There you go. And then this is a Claisen condensation. Claisen condensation. Okay, like that. So again, it's essentially a nucleophilic acyl substitution, except you end up losing the ester in the end. And then you want to take this compound, and I'm going to have to go over to a new sheet of paper here, but you want to go from this compound and you want to make this compound. So you want to make acetophenone. Okay, I want to make acetophenone, like that. So how are you going to do that? Well, what you would do is you would treat that with aqueous acid and you would heat that up, right? Because that would produce this intermediate, right, like this, okay, which is going to undergo a decarboxylation. And I told you that you don't have to draw the mechanism of this at all. That's okay. But you'd end up making this, doing this decarboxylation after you've hydrolyzed this to the carboxylic acid. And that is going to produce this enol. So draw the enol like this. My first curved arrow technically should go like this. Okay, like that is better. So I end up with this enol, which is then going to undergo tautomerization to give me acetophenone. Okay, so now once I've got the acetophenone, what it's saying is that they want you to take that and make this compound. So they want you to convert it into a Michael acceptor, like that. Well, how am I going to do this? Well, you're making an alpha beta unsaturated ketone, right? You have your alpha beta, so this is an alpha beta unsaturated ketone. So what would you use to do that? You're only adding one more carbon. This is the only carbon that you're adding, but you need to add one carbon here. So you only need a one carbon aldehyde. So you would treat this with formaldehyde, sodium hydroxide, and then you would heat that up. So again, this is a crossed aldol condensation, like that. All right, that's going to give you the alpha beta unsaturated ketone. And then after that, they want you to convert the Michael acceptor into this compound. So let me make sure I count my carbons correctly here. So you have 1, 2, 3, 4, like this. So essentially, you're adding 2 new carbons, right? You're adding these 2 carbons here. And so for that, you need a Michael donor to do a Michael addition. So this will be a Michael addition reaction. And your Michael donor would be a cuprate. So you'd use diethyl cuprate followed by treatment with acid, right, to produce the enol, which tautomerizes to give you the ketone. So once you've got that, the last thing they want you to do is to make another alpha beta unsaturated ketone. And it looks like this. So you want to take this compound, have the carbonyl here, and then you want to have another alpha beta unsaturated ketone. So you're going to want to do another crossed aldol condensation. And so in order to do that, since you're only adding one carbon, you would use the exact same conditions that you used up here. Identical conditions again. You would treat this with formaldehyde to add that one carbon, sodium hydroxide, and you would heat that up. And that's going to add the one carbon to the molecule. And since you're heating it, you're going to drive off water, and you're going to end up producing the alpha beta unsaturated ketone. So this is another crossed aldol condensation. And there you go. All right, and I think that's a really good question. So again, this is question 21. This is 21.73, which again I thought was a very, very good problem. All right, well, with that in mind, I want to look at one more problem before we get into some different type of chemistry today. And it's question 21.74. So 21.74. The first question So let me pull it up here. I don't have my textbook open. So we want to take acetophenone and we want to convert acetophenone into benzoic acid. So we want to make benzoic acid. And how are we going to do that? Because we end up removing this carbon. Could anybody tell me the name of the reaction you would use to start this sequence? Or does anybody have an idea where to start? Oops. It's got a name. It's a reaction I really like. Does anybody have an idea what reaction you might use here? It's called the Haloform reaction. So you might want to use the Haloform reaction here. Why? Because you have 3 acidic protons here. 1, 2, 3. And so you would treat this with sodium hydroxide, and then you treat it with iodine, and you treat it with a lot of iodine so that you end up making this compound where you basically convert the methyl into a good leaving group. So now it's got 3 iodines attached to it. So this here is now a good leaving group. And so now all you have to do is hydrolyze it, right? You're just going to take it and you're going to cook it up with acid, so H3O+. We're going to heat that up, and that's going to give us benzoic acid. Plus, you'd end up with this compound, CHI3, and that's called iodoform. So that's the iodoform reaction, or the haloform reaction. So haloform reaction. All right, 21.74b. So this is 21.74b. We're starting out with acetophenone again. So we're starting out with acetophenone like this. And here we're asked to provide the final product. That's what we were asked on the first one too. I didn't look close enough. So I had some notes written down about it. So he says you're taking acetophenone and you're treating it with bromine in acetic acid. Well, acetic acid is an acid, isn't it? Right? So it's the same thing as if you were to treat it in bromine and acid, right? So this is an alpha halogenation, right? Here's your alpha carbon. It's the one where the methyl group is. And so all you're going to be doing is adding a bromine there. So you're making nothing more than this. You're putting a bromine in the alpha position, just like that. The next one, 21.74c, says you're going to take your acetophenone and you're going to treat it with sodium hydroxide at an elevated temperature. So we're going to treat this with sodium hydroxide and we're going to crank that up like this. This is going to be an aldol condensation reaction, right? Because we're heating it, right? So we're going to have another equivalent of this compound, right? Some of them are going to be the enolate, but some of them won't. And so it's going to do a nucleophilic attack like this. So that's our connectivity, like that. Another way to draw the answer, to draw the final answer, is to do it like this. Let me show you my shortcut. I know I went over this with you in class. I want to show you again. So if I copy this and paste it here, okay, and then I'm going to paste it again. So again, this works best for an aldol condensation. So again, this is aldol condensation. So what I'm going to do is I'm going to erase this here, and I'm going to move the phenyl to the other side because we're going to end up with the less sterically hindered alkene. So I'll put the phenyl group over here, and then what you do is you take these 2 protons, or 2 of these protons, you're going to remove those and the oxygen, and that's where you're going to form your double bond. So your final product is going to look like this. You've got the phenyl, you're going to have a double bond to oxygen, you get another double bond here, you're going to have your methyl over here, and your phenyl like that. And that's your final product. So an aldol condensation reaction, just like that.